Okay, another way to evaluate limits is by looking at a table. So that's what we're going to do here. I've got a TI calculator. Go ahead and put this function into your into y1. Please make sure you put parentheses around the entire numerator and a set around the entire denominator. Okay, so we're going to look at the table, and we want to know what the limit is as x is approaching 2. Well, here f of 2 does not exist, okay? As we remember, though, it doesn't matter if the point exists. We need to know what's happening around it. We know that to the left of it, f of 1 is equal to 7, and to the right, f of 3 is equal to 3. That really doesn't tell us a whole lot because we need to get a lot closer. So what we're going to do is we are going to go to the table setup, which is second window, okay? And it doesn't really matter where we start, but we're going to go down to our independent variable and change that to ask, okay? And the reason we're doing that is because we want to be able to control what values go in, and it will evaluate for us. So let's go back to the table. So now what I'm going to do is I'm going to put in numbers that are close to 2 from both sides, and it's a little off the screen here, but that's okay. So I'm going to start with 1.9, okay, and then get a little bit closer, 1.99, 1.999, okay, and we can see that it appears that we're getting closer and closer to 4. Let's go a little bit further. Let's put 4 9s in here. All right, now, by the way, just putting in one number, not going to be conclusive. Make sure you're putting in a few numbers, okay? But we can see here that it looks like we're getting closer and closer to 4. As you remember, though, we need to approach the same thing for both sides. So let's look at some numbers on the other side of 2. So let's try 2.001, 2.00, oops, those aren't zeros, 0001, okay, 2.00001. Yeah. All right. Now at this point, it doesn't mean that it's actually 4. It means that we went beyond what the decimals that the calculator in the table will show, and so it just rounded here. Okay. But this does tell us that yes, we are getting close to 4 from both sides. So that means that our limit, is 4. And you can write down those values over here on the table if you'd like. Okay, so using a table is another way to evaluate limits. Just make sure that you are plugging in numbers that are very close to, and from both sides, you're very close to your constant. All right, and then the third method here for evaluating limits is to do so analytically. And when we talk about analytically in math, we're talking about usually algebraic expressions, okay? So, sorry. Okay, dog's barking. All right, we're going to add to this list of different things that we can do to evaluate limits analytically, but the first thing we want to try is, can we use direct substitution? Can we just plug in our number, our constant, into the function and get a value? Now, we need to be very careful with this because, as we have seen before, we don't care what the limit does not care what is happening at a point. It only cares what's happening around a point. So in order to use this method, we need to know without a doubt that the function that we are evaluating is it doesn't have something funky going on at that particular point. Okay, so for example, in this example, this first one right here, x squared minus 4x, that is, we know what that looks like. That's a parabola. Okay, on a parabola, there's no strange jumps or holes or asymptotes or anything like that. We know that it is a normal, if you know what I mean by normal, but it's a normal looking function. Okay, so for this one right here, it would be safe to go ahead and plug in 6. Okay, if we plug 6 into that, we get 36 minus 24 which gives us 12. So the limit here is 12. Now, could we check that by plugging in like 5.99 or 6.0001? Yeah, we can, but we can say with some confidence that x squared minus 4x doesn't have anything funky happening at x equals 6. On the other hand, it is very unlikely that a limit that we are asked to evaluate is going to be quite so easy because the goal is usually to be able to do some of the more complicated things, which is why we have our second option here. So our second option is we use algebra to somehow reduce it, and the reason that we need to reduce it is that or to manipulate it is that frequently we'll have an issue where if we try to evaluate with direct substitution, we get an indeterminate form, like 0 over 0. Okay, so let's look at this second example. If we try to plug 3 into that, I'm just going to put this up to the top to show what it's approaching. If we try to put 3 into that, we're going to get 9 minus 9 over 27 minus 27, which we know to be 0 over 0. 0 over 0 does not work. We cannot divide by 0, okay? And we definitely can't divide 0 by 0. Now, this does not mean that the limit does not exist, because this is just what's happening at the point x equals 3. We want to know what is happening around that point. So the way that we are going to handle this is we are going to look to see if we can somehow get rid of the factor that causes us to have the 0 in the denominator, all right? And if we consider x squared minus 9 and x cubed minus 27, we notice that both of those are factorable, okay? So let's try factoring those, and I'm going to use correct notation here. Until the step where I plug a number into the limit, into the function, I can't get rid of that limit notation. Like over here, I didn't put equals the limit as x approaches 6 of 36 minus 24 because I had already put the 6 in place of the x. So right here, since this will still be in terms of x, I'm going to write the limit. Limit as x approaches 3, and my numerator factors as the difference of squares. Okay, and the denominator is the difference of cubes. Look that up. Sorry, I just lost my train of thought because dogs started barking again. Okay, but we are factoring this as the difference of cubes. If you don't remember how to factor difference of cubes, that would be a great thing to look up. There's probably 30 YouTube videos that'll show you, or you can send me a message. All right, so we have x minus 3 times x squared plus 3x plus 9. Okay, and now we see that we have this factor x minus 3 in the numerator and the denominator. So I'm going to cancel those out. Okay, and now when I plug 3 in for x, I get 3 plus 3 over 3 squared plus 3 times 3 plus 9, so 9 plus 9 plus 9. And I no longer have the 0 over 0 problem. Okay, so my limit is 2/9. Just a note about algebra, in general we would not be able to get rid of a factor x minus 3 because it could cause a 0 somewhere, but the goal here was to get rid of the 0. So yes, we did need to cancel out the x minus 3's, okay? So if possible, look for a way to get rid of the factor that causes you to have the 0, okay? Here's another one. Limit as x approaches 2 of x squared plus 4x minus 12 over x squared minus 2x. This is the same one that we did above in the table, okay? But here we're going to do it analytically. So if we plug 2 into this, we would have 4 plus 8 minus 12, that's 0, over 4 minus 4, 0. So we know that this approaches 0 over 0, which again, we call that indeterminate, okay? So instead, we're going to look for a way to use algebra to eliminate the 0 in the denominator, okay? So keeping our limit notation, we can factor that numerator as x plus 6 times x minus 2, and factor the denominator as x times x minus 2. And then we have an x minus 2 in the top and bottom that cancel out. Okay, so limit as x approaches 2 of, and now I'm just looking at x plus 6 over x. I can plug 2 into that and I get 8 over 2, which is 4. And we know 4 to be the answer because that's one that we did with the table earlier. Okay? All right, for this next one, This right here is a little bit different. This is not one that we can use algebra to reduce. So if neither of these two options work, the next thing we need to do is think about what does the graph look like around our point in question. What would some numbers, like if I plug in numbers very close to that, what kind of output would I get, that kind of thing. So really, it's not necessarily formulaic, but we need to be thinking about what type of function it is, what the function looks like, okay? And this right here, we know this to be a step function. This is the greatest integer function, all right? Personally, I prefer to visualize the graph and then use the graph to answer the limit question. If you would prefer to plug numbers into that, you can do that as well. But I know that if I were to graph this, move up a little bit, if I were to graph this, I would have all the values from 0 to 1, not including 1, would give me an output of 0, and then it would hop up to 1, okay? And then again, I'd have a step like this. Okay, and I'm not really labeling everything here. I'll go ahead and put some there. There, I've kind of labeled my graph. This is just a sketch for me to basically write down my thinking. It doesn't need to be like a formal graph. But what I can see here is as x approaches 2, from the left, the limit would be 1, and from the right, the limit would be 2, meaning that the limit from the left and the right is not the same. So the limit as x approaches 2 from the left, and when you draw these, the notation our book uses is the double bar here, but normally when we write this, like in handwriting, we just do a single bracket, which is fine. Okay, so this is equal to, what did we say? From the left, it's equal to 1, which is not equal to the limit as x approaches 2 from the right, which is equal to 2. So therefore, the limit does not exist.